and it is distributed throughout the galactic halo, right? So this dark matter is occupying the region that we call galactic halo, and extends beyond the diameter of the galaxy. And when you do the calculation, in order to explain the observed rotation curves, how the rotational velocity depends on the distance from the galactic center, it turns out that we must have 5 times more dark matter than luminous mass. In fact, the notion of dark matter was introduced much earlier, way before mid-70s, by American astronomer of Swiss origin by the name of Fritz Zwicky. He basically came to the idea that there has to be some matter that does not produce the light, by observing how the galaxies in a cluster of galaxies called coma cluster move. It's a cluster of galaxies. These blotches that you can see here, they are individual galaxies in the cluster, and they are basically gravitationally bound to each other. So basically, I'll just sketch a few of those galaxies with their spiral arms, right? So they attract each other with the force of gravity. They tag on each other with the force of gravitational attraction. And as a result, they orbit some common center of mass. So they revolve around the center of mass of the cluster. Just like two stars bound by the force of gravitational attraction, or say a star in a black hole, revolve around the common center of mass, so the galaxies in a galaxy cluster are bound together by this force of gravitational attraction, and they revolve around the center of mass for the entire assembly. Okay? So what he noticed is that he noticed that they move too fast. If all of the mass in the cluster was contained only in their stars, the luminous mass. And he calculated by measuring the orbital speed, right? Again, everything is based on the third Kepler's law as formulated by Newton. He made a calculation how much mass there has to be for them to be moving as he observed, and he concluded that the luminous mass was only 1/400 of the total mass that had to be there. Okay? Therefore, he made the conclusion that there was, as he called in German, right, his native language, dunkle Materie, which is German for dark matter. Okay, so the term dark matter was actually first introduced by Zwicky, and it was all based on the observations of how fast the galaxies move in the coma cluster, way before the rotation curves of the galaxies were measured. And he was an extremely inventive person. He came up with so many things. For instance, he was the one to think that they're actually in the transition of a star to the neutron star, that has to be an event like supernova. That was proposed by him and another astronomer, Bode. He was a very demanding person and did not accept any kind of nonsense, so therefore he wasn't getting along with his colleagues at Caltech, California Institute of Technology, and he used to call them spherical bastards. And when asked why do you call them spherical bastards, he says because they look like bastards regardless of which direction you look at them, right? A sphere has a property that looks the same regardless of your vantage point, right? So that was the reason why he called his colleagues spherical bastards. And but nevertheless, he was extremely inventive, and well, I'll mention his name a bit later. Okay, so that stuff is there. So the question is, what is dark matter? And there were several proposals. One that is kind of makes sense immediately, they were called MACHOs. And this is an acronym that stands for massive, astrophysical, compact, halo objects. And there is a reason for this name, as you will find out later. So basically, the proposal was, okay, so these are things that do not produce light. So what could it be? It could be black holes. It could be the neutron stars whose beams of radiations are just not crossing us, and therefore we cannot detect them. There could be also old white dwarfs that formed long time ago and started fading, losing their thermal energy that was captured there initially. Then brown dwarfs, the star that never could quite become main sequence stars, right? Because they didn't have enough mass. For instance, Jupiter sized planets. Okay? So the question is, how can we detect a MACHO? Right? If it does not produce light, how can we detect it? And there is a very neat method that is actually based on Einstein's general theory of relativity, that any mass or energy bends space-time, and therefore if the light moves in that a bent space-time, it will actually curve around the massive object. Okay, and let me just explain what gravitational microlensing is. Okay, so this diagram schematically is explaining what gravitational microlensing is. So basically, if we are viewing a star from an observatory on Earth, and there is a MACHO, say a black hole, passing between the star and us, the mass contained in this object, say black hole, will curve the space-time, will curve the space, and the light will travel along the paths of shortest distance in that curved space. Okay? So it would appear to us as if the light from this star is coming from these two directions. Moreover, the image gets smeared into these arches. But the thing is that with objects that are not of very high mass, right? The amount of bending is not very large. If you have say a brown dwarf, it's a small mass, less than 0.05 of the solar mass, so the amount of bending of light is not large. So this bending angle, or the bending angles, are highly exaggerated in this diagram. They are typically 100 times smaller than the resolution of a Hubble Space Telescope. In other words, Hubble Space Telescope cannot resolve these small angles. So what one sees is when the light rays come into the telescope, you now get more light. And there is a brightening of the star. When the black hole passes between the star and us. So here is the star, and say this is the telescope, and this would be the line of sight to the star, and say a MACHO is passing between us and the star at some distance above the line of sight. So here is MACHO. It's moving with some speed v, and it has, say, some mass m, and it passes above the line of sight at some distance d. So when it's actually closest to this line of sight, we will receive most of the light from the star, right? These two images would get together and we will see a brightening of the star. So if I plot the observed brightness of a star, so I'm plotting here brightness of the star as a function of time. Once the MACHO is closest to the line of sight, I will see increase in brightness. So basically I would, when MACHO is at the closest distance to the line of sight. And the width of the peak depends on the speed of the MACHO, how fast it's moving, right? If it's moving very fast, then it will spend little time here, so the peak is going to be narrow. If it's moving slower, it will take longer for it to pass near this line of sight, and therefore the width of the peak is going to increase. And it also depends on the mass of the MACHO. And the height of the peak, how high it is, on this distance of closest approach. The smaller it is, the peak height is going to be higher. Okay? So by doing these measurements, by looking at these peaks of many stars in nearby galaxies, you can actually determine the masses of these objects, and you can detect them, so on and so forth. And there were several large international projects devoted to actually doing precisely that. And the results of these projects are that the MACHOs can account for only at most 19% of the mass of the dark matter. Okay? So clearly these massive astrophysical compact halo objects do not really can explain truly the origin of the dark matter. The second candidate that was actually proposed before MACHOs and influenced the name MACHO are WIMPs. And this is the acronym that stands for weakly interacting massive particles. And the theory behind this is that basically these particles have mass, quite substantial, much higher than, say, the mass of neutrinos, which have nearly zero mass, and that they interact with other matter in the universe only through weak nuclear and gravitational force. Okay? They do not interact with via electromagnetic forces, and therefore they don't couple to light, they don't produce any light. Okay? So the fact that they do exert gravitational force actually can then explain why the dark matter speeds up the stars at the edge of spiral galaxies, or makes galaxies in a galaxy cluster move faster than what you would expect based on the amount of luminous matter. Okay? But because they interact with ordinary matter only via weak nuclear force, they are very hard to detect. Okay? It's possible, but it's difficult. And there are several experiments throughout the world designed to actually detect these WIMP particles, and so far none has been detected. Okay? So in reality, we don't know what dark matter is. Okay? And it turns out that actually we know very little about the stuff around us. The composition of the universe, only about 5% is ordinary matter, the stuff we and stars are made of. 27% is the dark matter. And everything else, nearly 70%, 68%, is something that was invoked basically only since late 90s in order to explain the acceleration in the expansion of the universe, called dark energy. Okay? And we don't know not only what dark matter is, but we have no idea what dark energy is. So when you think about it, what we really understand today out of the universe is only 5%. There is a lot of stuff that we still need to discover.